Hello and welcome back to another episode of AP Basics with Base. Make sure you like that, drop a like, leave a comment below on this YouTube video. So today we're going to look at calculating the pH of weak acids in solution. Okay, so the thing we've gotten to so far is that weak acids do not fully dissociate, right? So we get this pattern that sets up. The acid HA goes to H plus A minus. All right. So, unlike strong acids where if you have a 1 molar solution of HCl, we know right away that we're also getting a 1 molar solution of H plus ions. We get this partial dissociation with weak acids. So, let's see how we solve these problems and how to calculate them. Okay, so let's say, I think the easiest way is just to look at an example. So, determine the pH of a 1 molar solution of acetic acid, and its acid dissociation constant is 1.8 times 10 to the negative fifth. All right, so let's go ahead and do this. So first off, I'm going to start with my chemical reaction. Now, I give you the formula here, so we could use HC2H3O2 decomposes into H plus acetate ion. But, like everything else, you could always use this general reaction too if you wanted to, if you feel more comfortable with that. So, let's put our ice chart in. It's at equilibrium, so we know we're going to have to use an ice chart to solve. And let's think of what we want. We want pH. So in order to determine pH, we need to determine the equilibrium concentration of H plus. So let's fill in what we have. We have 1 molar of this. We have 0 of this initially, 0 of that initially. So we're going to have minus x here, plus x, plus x. Then we're going to have 1 minus x, x, and x. Okay, so now that I have my concentrations at equilibrium, what I can do is I can plug those into my Ka. So the Ka is equal to the concentration of H plus times concentration of C2H3O2 divided by the concentration of acetic acid. Okay, so as I plug those in, let's see what we got. We have 1.8 times 10 to the negative fifth is equal to x times x divided by 1 minus x. Now, we're going to do something, and some of you asked me about this in class. If you were to solve this, what you'll notice, you'll have an x squared term over an x term. So if you were to factor it all out and everything, you'd have a quadratic you'd have to solve. But there's something that's called the 5% rule. And that is if x, okay, or the acid dissociation, the change is less than 5% of the initial concentration, then the equilibrium concentration, or in this case we're going to say 1 minus x, is about equal to 1. Okay, or close enough equal to 1 that it's not going to make a difference in the pH. So now, how do you know if an acid dissociation is going to be less than 5%? Well, one of the things that helps cue us in is the Kas. Okay, now this varies with concentrations as well, but we have a 1 molar, so that's a pretty strong concentration here. And my Ka is times 10 to the negative fifth. Well, if it's times 10 to the negative fifth, it's probably safe to assume that your x is going to be less than 5%. So let's go ahead and make this assumption here. So this simplifies my Ka. Now it's 1.8 times 10 to the negative fifth is equal to x squared over 1. What's a much simpler equation to solve? So I multiply through, solve for x. I'm going to square root both sides, and x is equal to, let me get my calculator out real quick and do this. Square root x is equal to 0.0042. So let's compare that. Is this statement true? Did less than 5% of it happen? Well, this is, x in this case is equal to 0.42% of 1 of the initial. So is this true? Yes, I can use this assumption. So what I would always do first is solve for x and see how does it compare to my initial concentration. In this case, it's less than 4%, or I have 99.58% of my concentration left at equilibrium. So we're going to say that is essentially equal to the initial concentration. As far as AP is concerned, about 99% of the time, you will be able to use this assumption. Okay, but I wanted to determine the pH. We're not quite there yet. So this is the 5% rule. Makes solving these really quite easy. So we come up with the concentration of H plus. H plus is equal to 0.0042 molar. So to find the pH is equal to negative log of 0.0042, which is equal to 2.37. Let's do another practice problem here. Let's determine what is the pH of a 0.5 molar solution of hypochlorous acid. Hypochlorous action has the formula of HClO, and its Ka is equal to 3.0 times 10 to the negative 8th. All right. So right here we have, okay, 3.0 times 10 to the negative 8th. That's a really rather small K. So I'm going to go ahead and make this assumption that the 5% rule is going to be true. I'm still going to set up my ice chart here, though. So HA, H plus A minus, .5 molar of that, 0 of this initially, minus x, plus x, plus x. And since I'm going to, here, 0.5 minus x, what I'm going to say is 0.5 minus x is about equal to 0.5. So I'm going to say that we're going to assume that the 5% rule is true because my k is so small, and then we'll check it real quick. So solve it now. I have my concentrations at equilibrium. I'm going to plug them into the Ka. So 3.0 times 10 to the negative 8 is equal to x squared divided by 0.5. Multiply 0.5 through to both sides, so we get 1.5 times 10 to the negative 8th, if my math is serving me correct today. And then I'm going to square root both sides of that. And x is equal to 0.5 times 10 to the negative 8. X is equal to 0.00012, or 1.2 times 10 to the negative 4th molar. Well, does this fit my less than 5% rule? Yes, that is less than 5% at 0.5. So you can always check it. You know, in this case, we're looking at 0.02%. Okay, so in other words, I have 99.98% of this left at equilibrium. All right. What would you do if it's greater than 5%? Say you check this here and say x was equal to 0.1. Well, that's more than 5% at 0.5. Well, then you need to go back through and solve it as a quadratic. Okay, but again, as far as AP is concerned, I've not seen a problem where they give you that. So we have our x value now. So now the final thing is negative log of 1.2 times 10 to the negative 4th, and that is equal to log of 2. The pH is equal to 3.92. All right, so there's how we calculate pHs from weak acids. All right, hope this was helpful. Remember, drop a comment below, smash that like button. See you guys.